is cover Laplace transforms using pairs. These are instead of having to figure them out using the integral definition, these are predetermined, prefigured out Laplace transform common pairs. And then we're going to figure them out using properties. So it turns out that if you tried to list every possible Laplace transform pair, you'd have a table that's the size of the room. So instead, the pairs just show a few simple cases, and then using properties, you can change around the problem that you're given and break it apart and modify it so that it can use the pairs, even if what you're given doesn't directly map onto a particular pair. And the ones that we're going to be looking at in particular, the properties, are going to be linearity, time shift. That's a very common one. We'll talk about differentiation and, of course, integration. And then last, we'll talk about, well, almost last, initial and final value theorem. And then very, very last, we'll review what step functions and impulse functions are. I don't think there should be. So that's going to be our contract then. And let's quickly go over what we started the last lecture with last time, which is this big picture that you're given some sort of input. We'll call it X of t. Maybe it's a voltage, maybe it's a current, maybe it's something completely unrelated, like a thermal energy input, or a stock market price, or the height of a booster rocket over the ground. And it's more complicated than anything we've studied so far in EE230. So it's not sinusoidal steady state. It's something like, for instance, 2e to the minus 3t u of t. So we've got that input, and we put it into our system. And it's called signals and systems, not circuit inputs and circuits, because what we're doing here generalizes far beyond just a simple circuit. So this could be any system that changes our signal from one thing to another. And then from that, we get our output. And we'll call our output, in general, y of t. So x of t in, y of t out. And you know from differential equations that if you describe your system using a differential equation, or if you describe your system using some sort of circuit, resistors, capacitors, inductors, you could find the output for that particular input using differential equations. And it would be hard. So instead, we're going to take the Laplace transform of it. And that Laplace transform is the first step that we're going to do. And so now we've convert our lowercase x of t into our uppercase x of s. And of course, this is just another equation, but it looks on first blush totally different than this 2e to the minus 3 u of t. I mean, it might, in fact, you know what it looks like for this. It looks like 2 over s plus 3. And then we rewrite what our system is in terms of its Laplace transform. We haven't talked about how to do that yet, but this is our second step. We'll be covering that in a couple of lectures. We'll be covering that actually next lecture. And now we find the output. We find the output in the frequency domain, which is, instead of having to do complicated solutions of differential equations, now it's just a multiplication. We multiply the input with the transfer function together and we get the output. Now look, you can't do this in the time domain. This is, there's a border here between what's are up here, it's time domain, and down here, its frequency domain. You cannot multiply your input by anything to do with the system in the time domain and get the output. The only way to do that is using differential equations. But in the frequency domain, you can. The frequency domain changes calculus into algebra. And then our third step is to take that inverse transform back. So this is our third step. And now we can find our y of t. So big picture, that's what we're doing. Any questions about that whole process?